Okay, ready, right? Tomasz, everything okay?
It's okay.
Okay, perfect. Thank you. So first of all, I think it's very nice and wonderful that we do this workshop. And I must say, I have really enjoyed this morning very much. I must also admit that I have a very hard time, maybe because I'm old, following, right? So I get distracted all the time. And then when I teach, usually I like feedback from the students, and this is not possible. So, so one thing for people here to make your life easier, I have here down here, I don't have page numbers, but I have here where I am, okay? This is the outline of my talk about basics, some results, and then it's all about scanning probe microscopy of oxides, okay? And also, so normally I like to ask questions in my talks, and so I will try to do this. So I will sometimes, 3 times, ask very simple questions, and then there will be this question mark blinking. And it would be really nice if at least some of you could put the answer in the question and answer thing. So I know that some of you at least stayed awake. Okay, let's try that. If it doesn't work, okay too, but it would be really nice. Okay, so let me get started, and let me get started with another Corona thing. So as Tomasz mentioned, I've been back to Vienna for 10 years now, and every year we go on the roof of our building and we take a group picture. But this year we had Corona. So this is the first group picture with social distancing rules obeyed. So everyone here is about 2 meters apart. And this works because we take a very strong lens. So it looks like we are right next to Stephansdom. Okay, so that's the story. And I tell you to introduce the people who did the work. So I should mention Martin Sedwin. This first time he's no longer the group picture because he moved to a new position in Prague. Margareta Wagner and Igor Sokolovic, and then very important, my colleague Michael Schmid. And then as it might get clear to you a little bit through the talk, it's very important to have theory friends. Those are our friends from the University of Vienna. All right, so this is the topic of my talk: surface investigations of metal oxide probed with atomically resolved scanning probe microscopy. Okay, so metal oxides, that means you have a metal atom, we talk atoms of course, and you have an oxide, an oxygen atom. Okay, so they come together and make a metal oxide, and then because the oxygen is very electronegative, it sucks away the electron from the metal. Oxygen is always in oxides, normally, formally, twice negatively charged. And I'm saying this because it's important for the electronic structure. So this would be the density of states of a typical oxide. So you have typically filled states, oxygen derived, empty states, metal derived, because the electrons are given to the oxygen. And then depending on many details, you have a more or less wide band gap in between. For the materials I will be talking about today, they're all a little bit N-type semiconducting, so the Fermi level is at the lower edge of the conduction band. Okay, so it's important to keep this in mind. It comes back later. All right, so we have not only one metal and one oxygen atom, we have a whole lattice. And why would we like to look at atomically resolved scanning probe microscopy? Well, a very important issue in oxide surface science are actually vacancies, defects, oxygen vacancies. So often an oxygen atom is missing. It would be really nice to see directly atomically resolved where this oxygen atom is missing. Also, you can have surface chemistry, you can have adsorbates, hydroxyls are very important. So you could have a hydrogen atom somewhere. It would be nice to see that one also. So, you know, people came up very early with the idea that it would be good to use scanning tunneling microscopy, and that would be the first part of the talk. And then more recently, we have started, and other people also starting this nice technique pioneered by Franz Giesibel, who gave the first talk earlier this morning, non-contact atomic force microscopy as well. All right, so when I say early, I mean really early. So, you know, before I start, our thing today, our material today will be this one, rutile TO2 110. You can buy nice single crystals. It's transparent, has a 3V band gap, so no visible light is absorbed. If you make oxygen vacancies, then it starts to turn a little bit light blue, and more vacancies, it becomes darker and then becomes N-type semiconducting, and then you can do STM if you wish. And the nice thing is that this is the atomic model. When you take out these vacancies, when you make these oxygen vacancies, they all are at one specific position. So here the oxygen vacancies all very well defined. So a wonderful system to study. And when I say early, I mean really early. So STM was invented in the 80s, 1990. This is the first atomically resolved STM image by Greg Rohrer, published in 1990. And my first question is, what is wrong with this image? So is it the size? I mean, there's some rows here, there's some rows here. Is it the direction, or is everything right? So please type in your thing A, B, or C. Okay, so the answer, actually both, but main thing that's wrong is the direction. So if you look, these rows here run in 001 direction, and here they run in 111 direction. So it turns out what these people did is they pounded on the crystal to make it really conducting, make it really, really, really dark. And when they made it really, really, really dark, the crystal itself changed. It made crystallographic shear planes, and actually those are the ones that they saw in these images. So atomically resolved, well, maybe not so quite. So this was 1990. Here comes this young assistant professor from the United States, 96, and published her first on paper on TO2 where this oxygen, so here the directions are right, see 001, and also here these oxygen vacancies, all right? So that's good. I should mention that normally these STM images are taken in constant current mode with a sample bias typically of 1.2 volts. So that means, again, density of states, here's the Fermi level, 1.2 volts, meaning we are tunneling from the tip into the empty states, okay? So this is also then clear. So it was always a comment, do you see the oxygen rows? Do you see the titanium rows? This was the first theory friend they published this paper with. This is the density of states. You can see the contours go down, empty states, where the oxygen sticks up, and up where the titanium is, and when there's oxygen vacancy, something extra bright. All right, so this was established early on. Let's go on. First of all, first take-home message. Important for atomically resolved STM, you need to know how to prepare the oxide surface, and it's also very good to have friends who tell you how to interpret your images. That's true up to today, actually. That's why we had Georg Resse and Cesare and Michele in this first picture. All right, good. So rutile TO2 let's go forward 10 years or so. Xiaochun Lim, a postdoc, published this nice image. And this is now a promise to these hydroxyls, right? So you can have OH groups. In fact, when you have an oxygen vacancy, then water will dissociate, will make an OH group and put the proton next door to the next oxygen. And then when you have a better, much better images, of course, 10 years later, here the oxygen vacancies, bright bumps here between the rows, and here would be a hydroxyl, all right? In fact, it turns out, to tell you the truth, this picture was not oxygen vacancies, these were all hydroxyls. So we didn't have good enough vacuum, so water came and, you know, filled up these vacancies immediately. Now, Xiaochun actually took a movie, so that's an STM movie, where a water molecule comes, mixed to oxygen vacancies, and then they diffuse apart. So this was about intrinsic diffusion of hydrogen rutile. So I play you this movie. You can see here is the water molecule coming, dissociated immediately, and then it's driven apart. Later it turned out because of presence of water. So when I've showed this movie very often, it's already now, you know, more than 10 years old, and people always ask me, how quickly can you scan? This was really slow, right? I think it took Xiaochun like 2 or 3 hours, frame after frame, every frame 2 or 3 minutes. Now, if I say state of the art, This is a really state-of-the-art movie in an oxide surface, a different one now. This is a magnetite surface by the people in Munich, Barbara Lechner and friends. Here again, you have these rows, here in case an iron rose. You have a hydroxyl. The hydroxyl changes the density of states, makes a bright spot. And then this hydroxyl hops back and forth in between. So here you can see that this is flickering. So it's flickering because these OH groups go back and forth. This I'm just showing you because this is in a state-of-the-art video frame up to 20 frames per second. So you can really in real time now measure these dynamic processes. So that's what one can do today. All right, now let me go to the next topic. And the next topic is, where are the electrons? Okay, so electronic structure. So I showed you before that, you know, we like to take these oxygens out by treating them in outer high vacuum, and then we have the oxygen gone, but there's 2 electrons around back, right? So where are the electrons? Next question to you. Please type in your question answer. Let's see if anyone does that. Are they anywhere, somewhere, or nowhere? Okay, I hope someone answered. So actually the answer is all of the above, actually either A or B. So they could be either delocalized, meaning anywhere. So you could have these electrons and really being like 2-dimensional electron gas. That's something people really like to look at these oxide surfaces and interfaces. You can tell that from the electronic structure, because what would happen is you can think of this empty conduction band moving down a little bit just below the Fermi level, and then you have very sharp density of states right here at the Fermi level. Okay, and with the state-of-the-art microscope, where you can actually then look at not only at empty states like I showed you before, but it's filled states, you can actually see where the electrons are. So this is a paper by Martin Sedwin from a number of years ago, also on TU2, but annotates. This is a empty state image, positive sample bias. This is filled state image. And this has been taken in constant height mode. So, you know, you cannot have a feedback if there's almost no density of states. And the nice thing you can do, of course, is SPM, is you can look at spectroscopy. So if you go across this line here, and then across this line, take spectrum after spectrum. So you sit here, take a spectrum, sit here, take a spectrum. The spectra look like this. And here you can see a very sharp peak. This very sharp peak, you know, 0.025 or something below Fermi level. This is really indicative of a dispersed, localized electronic state. And in fact, in field state images, you can see really how far they are. So people call this a large Polaron. All right, so they can be anywhere, but they can also be somewhere. So answer B was also correct. So it can be localized. So for example, they can localize on a neighboring metal atom, right? A metal ion. So instead of X plus, and it's then X, you know, like 3, 4 plus, it could be 2 plus, let's say. And then in the electronic structure is quite different, because then you get also not only in spatially, but also get here in energy, a very localized state that's in metal derived. And people call this state, and there's a lot of interest right now in these things. They call it a small Polaron. Okay, small Polaron. Why Polaron? It's quite easy actually. So if you have here, let's say 4 plus, right? And here the oxygen atoms, ions are surrounding it, and then you put extra negative charge, then the oxygens get a little bit repelled, right? So you have like a polarization clouds, a little bit repelled, and then they like localized there, and if it hops from place to place to place, it takes this polarization cloud with it. So they're called Polarons. You may wonder why I put this green dot here below the surface, not at the surface. In fact, because in our now already well familiar system, rutile TO2-110, it turns out, and there are many experiments that have shown that, also indications before, that these are extra electrons, calculated field density of states. This would be titanium atoms, surface atoms, lower atoms, and then some of these electron clouds goes above, so goes to this, it's localized, but a little bit goes to the surface, is localized on subsurface. This would be a simulated STM image, and this is an STM image in constant height again, just, oops, sorry, going with the STM tip, always half an hour tunneling distance in front of the surface, and then at this particular voltage, you can see minus 1.4 volts, so that's really deep in the 3D band gap, and then you can really see this signature of these two dots for the polaron that we have from the DFT calculations. So it turns out, actually, when you take more and more and more oxygen out, then at some point these electrons, you know, they like to be subsurface. They like to be in the first subsurface layer, but if you move too many of them, you know, you can't get a certain number. You can put one on every third one, so there's actually a little bit of ordering here. But if it's too many, then the system doesn't like it anymore, and the system reconstructs. So you can see that here. This is, sorry, something here. So here you can see these rows that have been observed very early on in TO2. We call it the 1/2 reconstruction. And the explanation is really, it's an electronically driven phase transition. So there's a certain number of electrons that come here. You can count how many vacancies you have. You have exactly 18% vacancies. Each one puts in 2 electrons. Then these electrons distribute. You get this 1/3 superstructure, and boom, the system goes back and makes these reconstructions. So Polarons, smaller, who cares, right? Well, actually, it turns out the chemistry people, they really care about this. This is a paper by Christoph Wöll and co-workers, where they have looked at carbon monoxide adsorbed on reduced R-TO2, so titanium dioxide that has these vacancies I told you before, and they did infrared absorption spectroscopy. So this is the intensity wave number. This is the vibrational stretch, CO stretch, okay, a CO stretch, and they could see two stretches, so 2 different frequencies. So here is a CO molecule, here's another one, and then this CO stretch frequency, one is 2178 centimeters minus 1, the other one 2188 centimeters minus 1. And then they said, well, you would think they said it's not in the oxygen vacancy according to their theoretical calculations. One of them has a polaron, so one of them interacts with this localized electron, so one of them is charged, the other one is not. Okay, we can look, right? We can do, this is a paper more recent, even 2019. So here you can see, this is 8 by 8 nanometer. Each bright dot here is a CO molecule. This would be the oxygen rows. This would be the titanium rows. You can see here in between in between 2 titanium rows, you have here these extra bright spots. This is actually CO molecules that like to go into these vacancies. Okay, they can be here. So this is a CO, this is a vacancy, this is a CO inside the vacancy, and then these are also CO molecules, carbon monoxide molecules, some with these triangles and some with these triangles. Okay, now you cannot see anything here, but if you look, and while you take this image where you look at the CO molecules, you also measure at the same time the tunneling current, -1 volt, so coming out, right, where the electrons actually are. You can actually see this triangle, all right, is darker and this one is brighter. So this is where the polarons are localized. Right? And without that, I wouldn't, if you're interested, you can read up this paper. Without just this image, I wouldn't see anything. But you know, these things really hopped around. So these electrons, these polarons actually hop from CO molecule to CO molecule. And actually in the STM, you don't even see these CO molecules here in the vacancies. So that was something people confused for a while. But it actually brings me up to my next topic. I have to hurry up. My next topic is this one here. Non-contact AFM. This, in fact, is a non-contact AFM image. It's not really an STM image. So this is really the frequency shift that Franz Giesebold explained really nicely earlier this morning. Okay, so non-contact AFM. We had all the introduction this morning. We know it's a frequency modulated sensor. We know we're in either repulsive or attractive regime, and we measure we oscillate with a certain amplitude, very small, and they measure the shift in resonance frequency. So this is from Franz's stuff. This is with us. Here is our UHV chamber. It's a 1-ton chamber. It hangs on these bungee cords. And the reason is that, remember my group photo in the beginning? The group photo was taken here. The lab is here. Not a very good situation for constant height measurements. So that's why we had to come up with this bungee cord system. So that works really well. It's very cheap, actually. And we have a little patent on it. Okay, so question. Last question. What does one need for atomically resolved non-contact AFM? I give you a tip. It's a 3-letter word and starts with a T. Okay, so the answer is tip, right? So this was mentioned already from Franz earlier this morning. These wonderful images people are getting are because they put a CO molecule at the end of the tip, are in repulsive mode. It doesn't interact, and this gives really super contrast, because if you have interaction between 2 atoms, you need to know what these 2 atoms are. And it turns out for oxides, for metal oxides, you get really wonderful atomically resolved images if you take an oxygen terminated tip. So this is a little model, a TO2 tip. If you stuck your tip into your TO2 surface, it will be covered with TO2, and then with oxygen at the end. Igor figured out how to do that really well here. I don't go into detail. This is an AFM image from oxygen adsorbed on TO2 in all sorts of different configurations. The nice thing is if it has a TO2 surface like this, you can just go there and snatch an oxygen, and then for sure you have an oxygen terminated surface. And then after many years, finally we can take a non-contact AFM in repulsive mode, and the oxygen atoms are clearly visible, and these oxygen vacancies are actually missing atoms. And just a very, very last slide that I want to share with you. This is some very recent work that we have just submitted by Margareta Wagner. It's a different surface, so not TO2, it's indium oxide 111. So this is the unit cell of indium oxide 111. It's a big spread structure, never mind. But the size of the unit cell, so this is 1.4 nanometers. It's really big. And if I remember right, there's 48 atoms in this unit cell. So this is exactly the same structure. Here the oxygen atoms are big, red, and here the indium atoms are green and blue, right? And you can see it's really many, many different atoms in many, many different configurations. So there's like 5 different types of oxygen atoms here. When you image this surface now with a oxygen terminated tip that you have prepared, like Igor did on TO2 with oxygen on top of it, in repulsive mode, you can actually see a alpha, beta, gamma, delta, alpha, beta, gamma, delta. So you can see this type of oxygen atoms. You can see they're really, each one is a little bit different brightness. If you take the tip, put a little bit OH, water on your surface, stick it in, and you have indium oxide and have OH terminated tip. So this is the same surface, not exactly the same area because I had to prepare the tip in between. But here you can see actually each of these dark dots corresponds exactly to one indium atom, the different ones that we have. You can even distinguish between the blue ones with a different coordination than these green ones. So this is it. I think I have left hopefully enough time for questions. So the new thing for us is non-contact AFM oxides. We have a lot of fun doing it. There's very new results coming out from our group and from other groups as well. And with that, it's your turn to ask questions. Thank you.
Okay, thank you very much for a nice instructive lecture. And I don't see any questions in the Q&A slot. So would someone ask question from people around? Seems that it's not the case. So I will ask you. So many years ago, it was some seemed to be very useful method, which was called atom tracking, where the tip was sitting somehow or stuck to an atom by a feedback, and then following it, and out of that you might evaluate, for instance, I don't know, activation energy, a similar parameter. So would it be useful in your case, or that method is more or less forgotten and not used?
It's not forgotten, not so much used anymore. I think with this very high frequency scanning, like I showed this very one moving video frame, you can actually take movies pretty quickly. I think one problem was always how much is the tip influencing things. So maybe if you scan across more quickly, then you can have maybe better ways of doing that. In non-contact AFM, you have to scan really super slowly. So for that one, so far, I don't think it would be possible to do that. But yeah, it's still around, but not used so much. I think people go more to this fast scanning.
Okay.
I have a question.
Yeah, please.
So can you say a few words on how you actually attach an oxygen molecule to the tip of the AFM?
Yeah, so that's, we usually have a different sample, right? So we can, the way to attach oxygen molecule is that we have a CO2 sample that we prepare, and we put oxygen there, and then we can see it, and we just go there and we go a little closer, and then it automatically goes to the tip. That's also how people attach the CO molecule, right? So the CO molecule, you know, people have shown this is also, you put CO somewhere on your surface, you go there and you go a little closer by either increasing tunneling current, tunneling voltage, and then it goes and attaches automatically. And usually the nice thing is that, you know, if you're really skilled, you can take this tip prepared on one sample and then go change the sample, land the tip, and it's still there.
So how long does it stay there? How stable?
Depends, right? Depends on the operator. If you're careful, it can stay for a long time. I mean, the whole thing, these non-contact AFM images are all taken at 4.2 Kelvin. So where things are really pretty stable. It's not so easy to terminate. It turns out that CO termination doesn't really work very well on oxides. But sometimes we want to have it anyway. And then what we do is we put a little metal cluster, platinum, let's say. They usually like to ball up. CO at room temperature doesn't absorb on the surface, but it goes to this CO platinum, and then it's like a little inkwell. We can go with the tip, snatch the CO, go and then use the CO to image things. So sometimes if you want to have CO terminated tips. So because it's a reciprocal process, right? Like here, you really need to know this atom on the surface, but also the atom on the tip.